Hello everyone, you are most welcome to LNT College Multimedia Studio. Today's our lecture is based on the chemistry of alkalides and electrides with a special focus on structure, synthesis, properties and applications. And the most important part of this topic is superalkali's behavior. So we are basically focusing on the chemistry of alkalides and electrolytes. As you know and previously learned about the chemistry of alkali metals like sodium, potassium, and rubidium, etc. So all the alkali metals actually exist in +1 oxidation state, right? So and because of the electronic configuration, suppose we have a alkali metal like sodium. So the sodium has a ground state electronic configuration. So this is the configuration of neon, and the outermost valence configuration is 3s1, right? So the in case of sodium alkali metal, the outermost valence electron, that is 3s1, right? So this 3s1 will be donated or it will be oxidized to gain the extra stability, right? So that is why you can say that all alkali metals, so because of presence of one valence electron in the s orbital, and so they are susceptible to donate its valence electron. So because after the donation, the electronic configuration, so that will be obtained, which will be similar to the noble gas configuration. So in case of sodium, so it has a electronic configuration like that, 1s2, 2s2 and 2p6, right? So because of the closed cell configurations, alkali metal cations are stable, right? And it can easily donate its outer electrons, right? So, and this is due to basically low ionization energy. So, all alkali metals are susceptible to donate its valence electron. Okay, so forming a alkali metal cations. So in the previous lecture, actually, you have studies about the complex formation tendency of alkali metal cations. So apart from that, we know that the alkali metal exists as M plus, right? So it means it has +1 oxidation state, and which forms complexes with oxygen donors. So that is hard donors in the structure. So they prefer hard metal cation. So it form complexes like that, M plus, right? And because of the negative charge or negative dipole present on the oxygen atoms, right? So they will act as a host for oxonium ions. So oxonium ions means hydronium ion H3O plus, right? So this is called oxonium ion or hydronium ion. So this can be trapped by these crown ether ligand, right? And will be stabilized by donating its proton or H plus. So it has host nature, so that can accommodate alkali metal cation as well as hydronium ion. So suppose this crown ether uh, trap potassium or sodium ion. So M plus in case of alkali metal, that is K plus, suppose. So the resultant complexes will be K18 crown 6, right, as a K plus. So this is called cationic complex framework. So this is called cationic complex framework, right? So this is stabilized by counter anions. Counter ions. So counter ions may be negatively charged ions or electrons, right? So in case of 222 cryptand, so this is the structure of this cryptand molecule. So actually they have oxygen donors as well as nitrogen donors. Both are hard donors, right? So they also prefer hard alkali metal cations. So suppose this can form the complexes with sodium plus or potassium plus or bigger size alkali metal cations like cesium plus. So the it also form a complex cationic framework. So similar to this is K222 cryptand plus, right? So there is a cationic complex framework in both case, in case of crown ethers complex or in case of cryptand complex. So they will form a special class of ionic solids. So that will be stabilized by uh, metal anions, right? So this is metal anion, this is sodium minus, and this complex will be stabilized by potassium anion, and this is called sodide ion. This is called sodide ion, right? And this is called potasside ion, similar to the sodide ion. And such type of ionic compounds where cryptates ions, they are stabilized in the lattice structure. So through the electrostatic force, and the lattice which contains sodium anion is called alkalide. And similar to alkalide, uh, electrides also form if the complex cationic framework, they will be stabilized by uh, electrons as a negative charge which occupy the lattice structure of the ionic solids. So either it is in free state or in solvated state. So here the electron negative charge act as a anion to balance the lattice structure of this cationic complex. So such type of actually compound, so that is a salt, and which is also a ionic salt, right? So a special type of ionic salt. So here negative anions is electron negatively charged, so this is called electrides, right? So this is called electrides, and this is these are called alkalides. So alkalide and electrides is nothing but it is a complex compound which forms through macrocyclic crown ethers or cryptand to form a ionic solid like structure which contains cationic frameworks as well as anionic frameworks similar to a salt, so like NaCl. So this is a normal ionic compounds, that is NaCl, which contains Na plus and Cl minus, right? So each cation is balanced or saturated by the anions, so to form ionic compounds. So here, because of the low ionization energy, either crown ethers or cryptands both have affinity to form a complex, so selectively depending on the size of the cavity, as you have previously heard about the cavity size in crown ether and cryptand. So if the size of the cations match with the size of the cavity of the cryptand or crown ethers, then stable complexes forms. So you know that the complex formation tendency of the ligands follows the stability. Non-cyclic open chain, non-cyclic open chain ligand, right? Open chain ligand will form less stable complexes compared to cyclic ligand. Cyclic ligand. So because of the chelate structure in the cyclic complex, so it forms stable complexes, and in case of non-cyclic ligand, they form open complexes. So the dissociation energy for the open complex is less than that of the dissociation energy of the cyclic ligand. And cyclic ligand means chelate or macrocyclic ligands. Chelating ligand like EDTA 4 minus, right? So this form stable complexes through the formation of chelate ring structure, right? Or it will be macrocyclic ligand like porphyrins or crown ethers or cryptand. So they form stable complexes like crown ethers, cryptand. They form stable complexes because of the formation of the chelate structure, right? So which requires more dissociation energy to break down the complexes. So they are highly stable. Okay, so in case of multidentate chelate complexes, so chelate complexes are actually formed by bidentate, tridentate, or multidentate ligands. So ligands are actually open in nature, so they also form a cyclic structure after the complexation. But so non-cyclic open chain ligands form less stable complexes than the chelate complexes, and chelate complexes will be less stable than the microcyclic uh, ligand complexes, and macrocyclic ligand complexes will be less stable compared to cryptand complexes. because cryptand has two type of donor atoms, so that is actually hard donors, nitrogen as well as oxygen atoms. And in case of uh, crown ethers, only oxygen atoms act as a donor centers for the complexation purpose. So what actually happens is that in case of alkalides, suppose we discuss about the alkalides, right? So alkalides is nothing but a type of inorganic or ionic salt which have structure M plus M minus, right? This M minus may be same as the cation or it may be different. Okay, so suppose we have a structure uh, in case of alkalides, so that is formed in case of sodium, right, when it is dissolved in diethylamine, right. So and in presence of 18 crown 6, it forms Na 18 crown 6. So that is plus and this is Na minus, right. So this is the ionic compounds which is crystalline, right. So that contains both Na plus as well as Na minus. So sodium cation, and this is what we call sodide anion. So in this case there is plus 1 oxidation state, and in the case of sodide ion there is a minus 1 oxidation state. So you can say that so such type of crystalline ionic compounds where both M plus as well as M minus exist in the lattice structure, so they have both oxidation state plus 1 and minus 1. So this is the beauty here is that the alkali uh, metals not only exist in plus 1 oxidation state, rather it also exists in minus 1 oxidation state. So this minus 1 oxidation state exists in the alkalides, right. So similar to the sodium, it forms through the potassium and or through the rubidium plus or through the cesium plus. So depending on the size and cavity of the crown ethers, so they prefer selectively the metal cations. So when sodium metal in solid state is dissolved in diethylamine, so in presence of 18 crown 6, they form such type of crystalline ionic solids where cationic complex form, so that is stabilized by electrostatically through the sodium anions. So in the lattice structure actually, so this sodium anion stabilize this structure. So here what happens actually is that one sodium metal donates its valence electron to the other sodium to form a sodide ion. So what is the beauty here is that here electronic configuration looks like neon, right. Here all cells are closed like 2s2, so similar to neon, so that is 1s2, 2s2 and 2p6, right. So in case of sodide ion, so here 1s2, 2s2, 2p6, 3s2, right. So s orbital is completely closed because of presence of additional electron, right? So, and this electron is loosely bound to the this anionic lattice, right? So this is golden yellowish in color. This is golden yellowish in color, right? So suppose the structural properties of sodium 18 crown 6 plus Na minus. Here sodium acts as a electron donor and another sodium acts as a electron acceptor. So this 18 crown 6, they are not able to accept the valence electron of sodium. So it is resistant to accept. So it is resistant to accept valence electron of sodium, right? Means such type of macrocyclic ligands, they are non-reducing, non-reducible, right? So if the macrocyclic ligand is have a resistance to accept the donated electron, or if it is non-reducible in nature, so only then such type of complex ionic solid is formed. So the only tendency of sodium is to donate its electron to the another sodium present in the vicinity of the lattice. So anionic site in the lattice, anionic site in the lattice A are occupied, sites are occupied by sodide ion, right? So overall, so such type of crystalline ionic compounds, so they have low ionization energy, right? Low ionization energy. And this compound is stable at -10 degrees centigrade, right? Or further, if it is cooled -13 to 70 degree centigrade, -70 degree centigrade, so they are stable uh, ionic solids. Here sodium exists as a Na plus, right? So Na plus, and another sodium exists as sodium anion. So both have closed cell configuration, right? So as previously you have seen that Na plus has noble gas configuration, and in case of sodium anion, so it has 3s2 in the outermost shell. So both have closed cell configuration. It means you can say that all the electrons are paired in these ionic solids. So such type of ionic solids are known as diamagnetic compounds. Diamagnetic compounds. So they are diamagnetic compounds, right? So if the solvent molecule, so they are evaporated and the concentration of the sodium cationic complex and sodide ion increases in the lattice structure. So actually then it is it becomes more condensed, more denser in the lattice structure. So this sodium or sodide anion, so may be free or it may be solvated, but because of the large size, so its size actually varies 2.5 angstrom to 3.5 angstrom. So the size of the anions or anionic lattice, so that occupies sodide ion or once Na minus K plus, sorry, this is not K plus. So this is actually potasside ion, and this is rubidiide ion, and this is synthesized ion, right? So if the complexation takes place through the sodium, potassium, and rubidium and cesium, then the counter anions, that is sodium anion, potassium anion, rubidium anion, and cesium anions, so their lattice size will exist in this range, means 2.5 angstrom to 3.5 angstrom. It means the Na plus, the size of the cation is lesser than the size of the anion. You know the chemistry of size variations. So cationic metals are always smaller than anionic metal or non-metals. Okay, so because of the additional electrons, so that will be uh, stabilized in the valence shell. So this is the size, and this sodium anion actually they will be solvated like that. Na18 crown 6 plus, and it may be loosely solvated through 18 crown 6 Na minus. So, but in practical, sodium anion remain in free state because of the large size, right? So this large size sodide ion does not reduce this structure. So they are active, they are reactive. So Na 18 crown 6 plus Na minus. So this is highly reactive. So highly reactive, it means alkalides are the ionic compounds that enhances the reactivity of counter anions. So such type of um, structure actually most important in the various applications. So that will be discussed in the next part of the um, lecture. So what actually happens, there is similarly sodium 222 cryptand, right, this Na minus. So this is golden alloys compounds, that is ionic compounds, so which is, and diamagnetics. This sodide ion does not react either cation or the ligand component, that is macrocyclic cryptand. So they are completely free, right? So this is the actually structure of the alkalides. So because of presence of this anions, so they are called alkalides, because only such type of complexes here are formed through the alkali metals, so they are called alkalides. Now if these complexes are, suppose we have actually bigger one cesium plus, right? So cesium plus form similar complexes, so that is actually cesium plus, so cesium, that is 18 crown 6, so it forms plus, and 222, sorry here, not 22, rather it is 18 crown 6 electron as a negative charge. So this anionic site either can be occupied through alkalide anion or electride, or you can say electron as a negatively charged. So such type of compounds where cationic complex, so that is stabilized through the solvated electrons, are called actually electrides. Electrides, because in the previous you have well known that once sodium is dissolved in ammonia, right, so they form electrides, Na plus NH3X and electron minus NH3Y. So this is also blue color solution, so that is electride. And in the previous lecture you have also aware about the electrides. So when the sodium metal in solid state, so they undergo dissolution in the case of liquid ammonia to form a electride structure. So this is this electride structure has actually solvated cation and solvated electron. So solvated cation means ammoniated sodium cation and ammoniated electron. So similar to the this analogy, as the solvent molecules solvate the cation and electrons, so this type of actually structures where cation is solvated through this crown ether molecule or cryptand molecule, and the anionic site in the lattice, they will also be solvated, but because of the bigger size of the anionic uh, atoms, so they are not uh, strongly solvated, so they may be free and they may be highly reactive. But if the counter ions, that is electron as a negatively charged, so this electron similar to the ammoniated electron, 18 crown 6 will solvate this electron in the anionic lattice, or this 222 cryptand, if it forms CS 222 cryptand plus and 222 cryptand electron minus. So in this case, 18 crown 6 will act as a ligand as well as solvent. So this solvent can solvate cation as well as electrons in the lattice. So this is monocyclic and this is actually bicyclic. So it stabilize the electrons or it solvate the electrons in the anionic lattice to form a ionic or crystalline solids. So both are crystalline solids. Crystalline solids. And this anionic site in the lattice actually occupied by negatively charged electrons. So they are not able to disturb the structure of sodium, or in case of cesium, cesium cation, or the structure of this ligand. So it has low affinity, right? So suppose this is again CS222 cryptand and electron negative charge in brief. So here electron is also that is solvated through 222 cryptand. So because of the low affinity, so this is your cationic complex framework. So this complex structure actually possesses low electron affinity. So it has low electron affinity, right? So this anionic site, so that is occupied by this electron, remain free or intact in the lattice structure. So due to presence of this single electron in the lattice structure, so they are paramagnetic. So overall, this electrides, so this electride actually they are paramagnetic ionic solids. So in case of alkalides and electrides, actually magnetic behaviors depends on the spin pairing effect of the electrons. If these electrons exist in paired state in the lattice structure, so they may be or they can form antiferromagnetic, ferromagnetic, or paramagnetic structure. So it will totally depends on the existence of the electron in the lattice structure. So sometimes this electron may be localized or delocalized, localized or delocalized, delocalized in the lattice structure. Okay, so if this electron is localized in the lattice structure, it means it has poor electrical conductivity in the lattice structure, and the compound, so that is actually electrides, so are slow electrical conductor. But if this electron is non-localized or it is delocalized in the lattice structure, so it forms very good electrical conductor. So it will act as a electrical conductor, electrical conductor if the anionic site which is occupied by this electron as a negatively charged is localized, delocalized in the lattice structure, so it forms electrical conductor. But another possibility is that if this solid or solution only it will act as a electrical conductor if this electron is free in the lattice structure and delocalized. But it may be chances that this electron as a anionic site, if this electron is localized fully, so then the magnetic property will be very, very low and different. So what is the possibility is that, so CS22 cryptands, cryptand, so suppose this is dimer and this is electron, that is solvated electron as a counter anion. So here in this case of this electride, so one cesium cation, actually they are sandwiched by two cryptand molecule. So they are sandwiched, CS, so they are sandwiched cryptand 1 and this is cryptand 2. So they are sandwiched, and this electron actually in the lattice structure they will be condensed or they will be localized. So because of the more complex, more denser structure of the lattice, right? So in this case, the compound is diamagnetic. Diamagnetic. So sometime electrides act as a paramagnetic and it may act as a diamagnetic. So depending on the structure of the lattice and stability of the electrolyte at ambient temperature. So most of the alkalides and electrides actually exist at a lower temperature. So in a thermodynamic and kinetic point of view, so they form a stable complexes actually as a ionic salt, and sometimes such type of complexes may be very labile, may be very reactive, right? So what actual property is that in case of such type of electride, this electron occupies approximate 2.4 angstrom of the anionic lattice. So the tendency to occupy in the lattice structure as E minus 2.4 angstrom of the lattice structure. So the size of this electron is lesser than that of any alkalide ion like sodium ion or potassium ion. So what about the lattice energy? Lattice energy, right? Because of presence of electrons as anion in the lattice structure and is smaller size, so overall the metal ligand and electron as a negative charge, it has less interionic distance, less interionic distance, right? So because of the small interionic distance between this cationic and this anionic electron, so there is a electrostatic interaction. So it forms ionic lattice. It has large lattice energy, right? But in case of alkalide, where sodium anion exists, because of the large size of sodide ion and large interionic distance between the cationic framework and sodide ion, so alkalide have low lattice energy. Alkalides have low lattice energy. So alkalides possess low lattice energy, whereas electrolyte possess little large lattice energy because of the size variation. In case of cesium 18 crown 6, cesium minus, this alkalide structure so is actually diamagnetic, similar to the sodium compounds, and once this form electrolytes and electrides, when it is formed, if the ratio of metal cation with respect to crown ethers or cryptand is actually in so this is actually concept like that. Suppose we have metal cation and cryptand, 2 cryptand, right? So if the concentration of this cryptand is very high compared to the concentration of this metal cation. Then there is a possibility to form electrides, right? Electrides. So electrides may be monomeric, dimeric, trimeric. So depending on the structural adjustment and thermodynamic factors. So what actually happens is that the compounds alkalide has larger activation energy. So in case of alkalide, 0.5 it is 0.45 electron volt. In case of electrides, it is 0.02 electron volt. The electrides actually possess very low activation energy. So it means electrides are actually very good electrical conductors. So it will conduct the electricity in the structure, right? Compared to the alkalide, where activation energy is very, very high compared to this value. So this is the beauty of actually the structure of the alkalides and electrides. Now, properties. What is properties? Properties. Suppose we have alkalides, like that is suppose we have sodium and 18 ground 6 plus and a minus, or suppose we have cesium 222 cryptand plus this is electron negative charge. First, both compounds are crystalline anionic compounds, right? And this sodide anion has lowest oxidation, that is -1 state in case of alkali metals, and because of the presence of bigger size lattice anion, the outermost extra added electrons, so they are not strongly bound with the lattice structure or cationic counterpart. So it possesses low ionization energy, right? So this electron, in case of electrides, also not able to destroy the lattice structure of this cationic framework. So this is since free or in a state of free radicals, single, so it can be donated so easily. So it both structure possess low ionization energy, or simply you can say these structure possess low work function, right? So this is the beauty. And if the low ionization, even in case of all alkali metals like sodium, potassium and rubidium, the ionization energy of alkali metals, whatever value previously we have dictated, the ionization energy of such type of structure where anionic lattice occupied by sodium anion or electron anions, so possess low ionization energy and compared to neutral alkali metals. So because of low ionization energy, they are highly reactive and they will act as a strong reducing agent. Strong reducing agent. So such type of actually compounds are very good reducing agents. Suppose we have a examples for where alkalides and electrides work as a reducing agent. So this is the actually uh, application of the electrides and alkalides. So suppose Birch reduction in organic chemistry you have heard. What is the Birch reduction? When we have a di um, or a aromatic structure, that is benzene. So in the organic chemistry, what happens actually is that, so this is reduced in the presence of sodium in liquid ammonia in the presence of ethanol, that is ROH. So the product is actually dienes. So once this sodium in liquid ammonia will act as a reducing agent. And what is the resultant effect? There is one double bond is reduced. Here 3 double bonds and here only 2 double bonds. So because of the hydrogenation, right? So this point and this points undergo hydrogenation. Hydrogenation. So the yield of the product either major or minor, so it can be decided by the reactivity of the reducing agent. So this conversion actually facilitated through the application of electrides, right? So in place of sodium in liquid ammonia, we can use here electrides, right? So this electride actually reduce this benzene structure to form dienes. Similarly, naphthalene can also be reduced. So this is the actually advantage of electrides. And another thing is that suppose this is your CS 2 cryptand plus and this is electron negative charge. Because of low ionization energy in such a ionic lattice, such type of structure actually is called super alkali Kali, kalis, super alkalis. So electrides are actually super alkalides, uh, which is a cryptates cation and electron as anion. This is called super alkalis. Super alkalis, right? Low ionization energy. Low ionization energy. And another advantage or another properties of the this electrides is that actually uh, they are hyper they possess hyperpolarizability. Polarizability, just for sake of the simplicity. So actually hyperpolarizability, hyperpolarizability. So electrides actually possess hyperpolarizability, right? So another thing is that so because of the hyperpolarizability, so they are strong and potent uh, candidates for the application in catalysis, optics, and electronics, and as a magnetic materials applications, right? So this is the actually beauty. And one another aspect is that what is actually the property is that so such type of actually behaviors are actually obtained in the case of alkalides and electrides. So this electrons actually remains in the solvated state similar to the uh, electrides in case of sodium in liquid ammonia as ammoniated electron. So this is the chemistry of the actually alkalides and electrides. So depending on the size variation or cavity variations, uh, there may be variety of alkalides and electrides through the complexation of the alkali metal cations and the crown ethers or cryptands. So crown ethers and cryptands actually they form more number of complexes which are thermodynamically stable sometimes at ambient temperatures, and variety of applications can be performed. So because of the um, enhanced property in this structure, so some types um, actually electrides are also able to reduce metal ions to produce metal. So these electrides are used as a reducing agent for the preparation of metal solids. Okay, and another one is that so sometimes alkalides are formed through the application of alloys. Suppose we have a potassium and sodium alloys, right? So if potassium sodium alloys they are treated with the cryptand, then what actually happens? K222 cryptand. So that is as a cationic framework, and the counter ions, that is sodium as a sodium anion. So the beauty of the uh, this class of compound is that, so if we have a different alkali metals as a alloys, then it also form alkalide compounds. So suppose this cryptand molecule is added to the solution of LiS, that is potassium sodium. So potassium is solvated strongly through the cryptand structure and exists as a cationic forms in the lattice, and the sodium, so that is actually uh, stabilized as counter ions as a sodide anion. So this alloys actually uh, so produce alkalides. Alkalides. So this is the beauty of actually the alkalides and electrides. Now based on the structure, so we can develop and produce variety of alkalides and electrides for the applications. Suppose in the practical chemistry, actually uh, we have a metal that is alkali metals. So when it is uh, dissolved in organic solvent, they are not soluble, right? So if one cryptand or crown ethers are added, and if it is shaken in the separating flask, so the cation will come from the organic part to the cryptand structure. So this is actually through the complexation behavior of the crown ethers or cryptands. So this is actually included as a advanced part in this structure. So what is the final conclusion is that alkalides exist as plus M minus, and electrolytes exist as M plus E minus. So this is your electrolytes and this is your alkalides. And depending on the structural variations and their stability, actually, so they can be used in various field, or simply you can use in the material science for the material designing's purpose. Okay, so this is the way and this is the understanding from my side. So in case of alkalides and electrides. So thank you for watching this video lecture, and if this video lecture is comfortable to you, please like, share and comment on the video. Thank you.